This is Suvarchila working as an associate professor, Department of Computer Science and Engineering, Ministry of Aeronautical Engineering. As a part of the database management system lecture series, in this session, I'll discuss about the functional dependencies and the Armstrong axioms to reason on FDs. As part of the database design, the requirement analysis, conceptual design, logical design, schema refinement, physical design, security design is there. We discussed already how the requirements are going to be collected from user or enterprise needs. And conceptual design, this is a high level design described by using entity relationship model. And we converted this ER model into relation schemas, and that is logical design. We discussed already the converted and the translated, in other words. Relation schema may not be in a proper manner sometimes. It may be facing some problems because of that redundancy has been increased, or high redundant data might be there actually. To avoid that, we have to refine these schemas. Whichever the schema we got from the ER model, we need to refine it to make our database in consistent state a longer period of times actually. So the schema refinement ensures that the database which we are going to construct will satisfy all properties of the database, integrity, controlling redundancy, everything actually. That verification is going to be done in the schema refinement step. This schema refinement step removes the inconsistency will be removed to make your database in consistent state, and the techniques are used to make our database in a consistent state is normalization. So we discussed already in the last sessions the evils of redundancy, repetition. Because of repetition, various problems we were facing, and the solution also we identified as a decomposition. Decomposition also must be lossless join decomposition. If it is any decomposition is having some lossy tuples or any spurious tuples are there, then the problem is going to be erased because of that decomposition also. Actually, we are using this decomposition technique for reducing any problems in our database design actually. But if the decomposition itself is not proper, then what happens? Again, the database design is going to be considered as a bad design actually. So it must be lossless join decomposition, because if it is in a lossy decomposition, spurious tuples are going to be resulted. In last session, we discussed about how the decomposition is going to be considered as a lossless join decomposition. So no spurious tuple should be generated by doing natural join of these decomposed relations. Then our decomposition is lossless join decomposition. So non-additive or losslessness of the corresponding join must be specified, as well as the preservation of the functional dependencies. These two must be considered at the time of decomposition. So we already considered about this losslessness, because to avoid this lossy decomposition or to avoid these spurious tuples, we have to consider one of the subrelation should have the common attribute as a candidate key. So the common attribute as a candidate key must be there. So in such cases, the decomposition will be lossless join decomposition. No spurious tuples are going to be generated, as well as there is no lossy of information also. The second one we have to consider preservation of the functional dependencies. Before that, we need to consider what is functional dependency. That we will discuss in this session actually. Whenever we are doing this decomposition, the property A is extremely important. That is non-additive or lossless join decomposition is Very much important. We cannot sacrifice it. Always we supposed to check the decomposition is lossless or not actually. If any lossy information is there or spurious tuples are generated, we have to take care of that at the time itself. But the second property may be a little bit considered as sacrificed, we may consider, or in other words, in certain cases, the second property may be having a that much important, stringently we need not consider actually. Less stringent we can consider. Sometimes it happens. Depending upon the normal form, we are going to consider the second property, preservation of dependencies are going to be considered actually. So these are the spurious tuples. Last class we considered when we are ABC decomposing as a R1, R2 relations and we are getting excess tuples, the red mark which we have shown to you, those are considered as a Pantheon records. Not all decompositions of the table can be combined using natural join to reproduce the original relation. And if you are considering by using a natural join, R1, R2, and here also we are making it as a R1, R2 as a ABC and BCD, then the tables R1, R2 are the same, however, the tuples 2 to 6 in R1, but not present in the original R1 actually. So these two tuples are going to be considered spurious tuples. So we have to take care of that decomposition does not generate any spurious tuples actually. Our natural join of the subrelations must provide us original relation. Coming to the next property, dependency preservation. So dependency preservation means here, what is dependency actually? These dependencies, various kinds of dependencies we'll discuss. Among them, the first category of dependencies are functional dependencies. We'll discuss about the multi-value dependencies, joint dependencies, various dependencies are there. Today we'll discuss about the functional dependencies. A functional dependency, X determines Y. We will represent by using a notation X, Y holds over a relation schema R. For every allowable instance R of R, T1 belongs to R, T2 belongs to R, then the tuples of any instance of tuples, if T1 is equal to T2, then some attributes, the remaining attributes, Y attributes of the T1 must be equal to T2. Any two tuples, if you take from the relation, two sets of attributes we are considering X, Y. We will say X determines Y means for any pair of all pairs of tuples, for all pairs of tuples such that if X is having equal values, then Y should also have equal values. Here this X and Y may be a simple tuple or it may be sets of tuples. So given any two tuples in R, if X values are the same, then Y values must be the same. This condition must hold good for every legal instance of relation R. Then we can say X determines Y. X functionally determines Y. Or Y functionally depends on X. Either of these two words we can use actually. So whenever we are using these functional dependencies, these FD is nothing but a condition, in other words. It's a statement or a condition. But all allowable relations must be identified based on the semantics of the application. So how these FDs are identified? Sometimes it may be business rules. The dependencies are going to be provided by the organization rules also sometimes. Or sometimes it may provide based upon the logical applications of the applications of the database design. We can consider these functional dependencies. These are identified based on the semantics of the application, that is logic of the application, or it may depend upon the business rules also sometimes. So given some instance R1 of R, we can check if R1 violates some FDF, but we cannot determine F holds over R. So every time it must holds good. It's just like in a constraints you can say. So every instance must satisfy these FDs. By discussing this concept, we may recollect our keys. What is a key? Key is a simple attribute or set of attributes such that all other attributes determines. That is, if key value is equal means the other values are also must be equal. It's a trivia because uniqueness no key. So that's why key is considered to be as a key determines all attributes of R. Then K is a super key of the R. And if it is minimal, then other keys will come into the picture. So we may consider FDs are generalization of keys actually. We'll discuss further how it is going to be defended actually. Functional dependencies allow us to express constraints, conditions that cannot be expressed by using either super keys or candidate keys, etc. Sometimes those are not keys because application dependent, no, sometimes. So that's why in such cases, we may express by using these functional dependencies. Generally, the key, primary key you are considering, candidate key you are considering, those are considered as a trivial dependencies. We'll discuss further. For example, in our banking loan relation schema, if you are considering, loan number determines amount. If two tuples are having the same loan number means the respective amount must be equal because amount depends upon the loan number. Our loan number determines how much they are supposed to pay. Similarly, each branch will have some loans. No? So loan number determines branch name also. In other example, in your student database, hall ticket number. Hall ticket number determines the year of joining. Hall ticket number determines their branch also. Because your hall ticket number consists of the combination of all these things. Based upon that, you can determine actually. But loan number need not determine customer name because customer may have more than one loan. So that's why if loans are going to be different, customer names are not going to be, need not be different actually. And loan number is the name, same. Maybe joint accounts may be considered. The customer names are going to be different also. So for example, we'll consider here, you observe here, loan number determines amount, loan number determines branch name, loan number does not determine customer name based upon the instance which we explained to you. That is loan information is there. So branch name, loan number and customer name, amount is there. You observe here. If loan number is there, two tuples you observe L001, L001. So if L001, L001 is the two loans are equal means the respective branch names are equal. And the respective amounts are also equal. You take every pair actually. So when you are considering this, loan number L001 is having three tuples, but customer name in the previous example, the color example, if you are going to consider, the first customer is Peter, second customer is David, and third customer is Mechan. But the respective branch names you observe, the branch names are same for all these things. That is, you consider any pair of tuples for which the loan number is equal, the respective branch names are also equal, the respective amount is also equal in the first example. So that's why the two constraints, that is the functional dependencies, loan number determines amount, loan number determines branch name, are valid, and the loan number determines customer name is an invalid dependency. But we will take another instance of the same relation. Loan information relation, we are considering another instance. So another instance we are considering here. So when you are considering the another instance, then depending upon the instance, the attributes or dependencies are going to be changed here. So the reverse of the FDs are going to be considered in this instance. Branch name, loan number, customer name, amount. So if amount is equal, loan number is equal. You observe. But loan number is equal, amount is not equal. You observe. Tuple in the second and third tuples, loan numbers are equal, but the amounts are not equal. So that's why reversal. Reversal means amount determines loan number is valid. In this instance, I am talking. In this instance. So similarly, a branch name determines loan number. If the two branch names are equal, means two tuples are having the same branch name, the respective loan number determines. So customer name determines loan number. That is also valid in this example. So the FDs are going to be the relation schema, which in the instance, in the first instance, the first set of FDs are valid. The second instance, if you are considering the reversal order of the FDs are valid. So what does it mean that? If an instance legal relation means always our FDs must be satisfied. Then once an FD satisfied, the reversal FD need not satisfy. A determines B satisfies. Doesn't mean that B also determines A actually. It may or may not. It depends upon the respective processing actually. So what is the purpose of these functional dependencies? These functional dependencies are used to test the relations to see if they are legal under a given set of FDs or not. Legal means they are satisfied. If a R is a relation, legal relation under a set of FDs F, we will say that R satisfies F. Set of functional dependencies we will represent with a uppercase F. Smaller we will represent, for instance, of relation schema. It's not schema. Bigger is relation schema, instance is smaller. So that's why when we are using these functional dependencies, to always test whether the set of FDs are satisfying on the relation R or not, the instance R or not, then it is legal instance. And it will specify the constraints on the set of legal relations, and all legal relations on R satisfies the set of the functional dependencies F. So that's why depending upon the instances, the set of FDs need not be changed. So whenever any updates we are doing or updations or any modifications we are doing, whether the respective FDs are satisfied or not, that will be tested. It discovers all dependencies between attributes because only keys are going to be determining the dependencies among the key and non-key attributes. But some other additional dependencies are there. Those are going to be identified through these functional dependencies. And also, if you could not able to identify keys also, by using these FDs and reasoning on FDs, we can identify keys of the relation also. Depending on, if you have a set of FDs, you can identify what is the key of that particular relation. If you have a schema as well as set of FDs, you can identify what is the key of that particular relation. And also it enables the good decomposition of the given relation. Good decomposition means lossless decomposition. For example, if you have FD, A1, A2, etc., AN determines B1, B2, etc., BM, the left hand side we are going to consider generally the values are going to be attributes, set of attributes determines uniquely the right hand side, in other words. So the left hand side set of tuples uniquely identifies the right hand side set of the tuples. Remember, it doesn't mean that LHS values compute the RHS value like in mathematics. It's only determines uniqueness we are specifying. So based upon the left hand side, right hand side cannot be, values are not able to compute. This is not related to that concept actually. Now These are the questions we may get. Does primary key implies functional dependencies? Then which type of functional dependency? If yes. Does unique key specifies functional dependencies? What type of FDs? Similarly, does functional dependencies implies keys? How? Any key, whether it may be a primary key or candidate key or a super key of a relation R, functionally determines all other attributes of R, all attributes in other way, all attributes of R. That means a key determines all attributes, no? So that's why it comes under a functional dependency. So primary key or candidate key, whichever may be the keys are there, we can represent or code it as a functional dependency. Each key implies FDs. Similarly, from FDs, we can determine keys also. So, if you know keys, you can write some FDs. Similarly, if you have FDs, set of FDs, from that you can generate a key also. We'll discuss that in further sessions. These FDs will have some properties. One of the properties we'll discuss today, and remaining properties we'll discuss during the time of normalization. The most important property is a trivial dependency. When will you call it as a trivial? Trivial dependency means any attribute determines itself. For example, an attribute A determines itself. It's quite trivial. So two values of A is equal means automatically the two values of A are also equal. No? So that any attribute determines itself. That is one kind of trivial attribute. Another kind of attribute, if A determines B is trivial means B is a subset of A. So I consider it itself means proper subset. It's not a proper equivalent because you observe here. We are considering it as a contained and contains. So A determines B is a trivial FD if B is a subset of A. Subset or equal, both. So a functional dependency is trivial if it satisfies by all instances of the relation. I'll give an example here in the previous loan schema. Customer name, loan number determines customer name. It's quite natural. If the customer name, loan number combination is equal means the customer name must be also equal, no? So that's why it determines customer name. Customer name determines customer names itself. The first example is proper subset. Second example is B is contained in A. And second example is equality. So, when we are having such type of functional dependencies, you can use the trivial dependency also. Sometimes it requires. Some more properties are there, partially dependency, total dependency, that is completely, fully functional dependency, that we'll discuss during normalization. We'll discuss some examples here. Constraints on entity sets. Consider a relation schema, hourly employees, social security number, name, lot, rating, wage per hour, that is wage rate, and hours per week. We may use directly when you are representing any functional dependency, you can use directly the attribute names as this, or you may rename with some domain names also, no problem. For example, I may use SSN name lot directly, or I may use as a S, N, L, R for rating, W for wage rate, and H for hours, number of hours per week. Both are valid. It depends upon the books which we are referring actually. All attributes of a relation by using the relation name, that is hourly EMPs, or we may use by using the respective domain names as a set also. So what are some FDs of this relation, hourly employees? Some FDs of this relation may be considered as a social security number is a key in this example. So social security number determines all attributes, that is social security number itself, as well as name, lots, and we are considering as a wage rate, number of hours, etc. Because it's a key do. So key means automatically you are going to consider the social security number determines all other attributes. Definition of the primary key. P, because already underlined, no, it's a key. So that's why you can consider it is a key attribute. Because of the key attribute, one functional FD was generated. Another one. You're going to consider here the respective attributes are going to be wage rate is there, rating is there. So there is a relationship between rating and wage rate. Rating determines as wage rate. Depending upon the rating, wage rate is going to be defined. Another functional dependency. Lot determines itself. L determines itself. It's a trivial dependency. So these are some of the FDs based upon our logic or semantics or rules, business rules specified on the given relations. Once if you have a set of FDs are given to you, we may generate some new sets of attributes also by using certain rules actually. We will call it as a reasoning. Reasoning about the functional dependencies. Reasoning means we will apply certain rules on existing set of functional dependencies and we will generate some more FDs. So these are because of the existing FDs were a new set of FDs are going to be generated by us, satisfying certain set of rules actually. For example, we have some functional dependencies. Title determines studio, star. Title determines studio is one FD and title determines star is another FD. We can decompose it actually. Title determines studio and the title determines star. Individual functional dependencies are there. If left hand side is equal, then we may combine them. We can consider as a union. Title determines studio star. But remember left hand side is equal, then only it is valid. Title determines studio. Studio determines star. Implies title determines star. It's a transitive. Satisfies the transitive property. But you observe another one. Title star determines studio does not equal into title determines studio and star determines studio. Because the decomposition on left hand side is not at all valid. Decomposition on right hand side is valid. This type of reasoning, based upon this reasoning, another set of or new functional dependencies are generated, which doesn't have any much additional dependencies on your original relation. This automatically satisfies based upon the original FDs itself. So an FD, F is implied by set of functional dependencies F. If we have F holds, whenever all FDs are in F holds. That means when we are having a set of FDs which are already hold on a given relation R, if you are generating more FDs from that F, if this F is hold on a R means automatically the generated FDs are also hold on F because these are based upon the existing one only. These are not new. So that's why this automatically holds actually. So we'll define based upon this reasoning, we will define what is a closure of F. The given set of functional dependencies F, there are certain other functional dependencies that are logically implied by F. This set of all functional dependencies implied logically from F is known as closure of F, which is represented by F plus. So what is F closure? F closure means the set of functional dependencies determined logically from the existing or defined set of functional dependencies F on a relation schema R. We can compute F closure by using some rules as a specified. Reasoning means some rules have to be applied. No, what are the rules we will apply? Those rules are known as inference rules. By using set of inference rules, we will compute F closure for a given F on a relation R. So what are these rules of inference? Three basic rules of inference are named. Those are known as Armstrong axioms: reflexivity, augmentation, transitivity. These are the basic inference rules proposed by, we will consider it as a Armstrong axioms. Let X, Y, Z are sets of attributes, may be single attribute as we are discussing from the beginning of the FDs, or it may be set of attributes also. X, Y, Z are sets of attributes. Then what are these rules specifies? Reflexivity means X is contains Y. Then X determines Y. That is, X is superset of Y means there is a functional dependency from X to Y. In other words, if Y is a subset of X, then X determines Y. It's a trivial dependency only. Reflexivity means it is a trivial dependency. So, if Y is subset of X, then X determines Y, FD can be added. For any such type of all trivial dependencies can be generated. Augmentation. Augmentation, if X determines Y, then we can add some more attributes on both sides. XZ determines YZ for any Z in your R. Z may be set of attributes in R, remember. Transitivity. If X determines Y, Y determines Z, then X determines Z. These three are the basic rules, which I explained by using simple example, previous slide. So, based upon these rules only, all those generation of the or logically inferred functional dependencies were generated. These are known as Armstrong axioms. These axioms are sound and complete inference rules for FDs actually. That is, sound and complete means by using these Armstrong axioms, we can compute all FDs logically inferred in F plus, and only those FDs only can be generated. New FD cannot be generated. So that's why these axioms are easily proved that those are sound enough to compute our F plus, as was complete means only FDs in F plus are able to compute by using these rules of inference, Armstrong axioms. These rules of inference or Armstrong axioms are repeatedly applied on our set of FDs, given FDs F, so that we will get F plus. Instead of applying these rules continuously a number of times, sometimes repeatedly can be considered by defining some additional rules. These additional rules means from the existing Armstrong axioms only, the base rules only are used to get these additional rules. Union decomposition. X determines Y and X determines Z means X determines YZ. This is union rule. So union rule means we are going to consider, based upon the reflexivity and augmentation properties, union can be generated. Similarly, decomposition. X determines YZ means X determines Y, X determines J. Remember, the decomposition or union are applicable on right hand side only. Left hand side set of attributes cannot be considered for this purpose. These two rules are going to be generated by using our basic Armstrong axioms. These can also be used hereafter to find our closure. So, for example, here CID, SID, JID, DID, PID quantity value are given, and C is the key attribute, then automatically C determines all other attributes. So project purchases each part using single contact. So product and the respective J can be considered. JP determines C. C is a single contact person ID. Department purchases at most one part from a supplier. So supplier and department determines your product. So what is the problem here? The problem is that SDJ is a key for that particular contracts only. So when we are using this, JP determines C, C determines this attribute, set of all attribute being a key, and implies JP determines all other attributes. That JP is also a key because by using your transitivity property, three attributes are identified by us. Three FDs are identified by us. C determines CJ, DP, QV, and based upon our business rules, project purchases each part using single contact and department purchases at most one part from the supplier. These are the constraints provided by the organization. So based upon this, we got a functional dependencies. JP determines C and SD determines P. S is your ID and supplier ID and D is the department ID. By using these three FDs, we will generate one more FD using transitivity property. Based upon this, what we got? JP is also a key. So basically C is a key, but JP is also key means it may be a candidate key. So SD determines P implies both sides if you are adding J, SDJ determines JP. So automatically SDJ also by using augmentation, SDJ determines JP, JP determines CSJ, DP, QV implies SDJ determines by using transitivity property. So because of this, what happens? Your SDJ becomes again key. By using property, JP become key, SDJ become key. This is a super case here. So like that, by transitivity, does SDJ become a key actually. So from a given set of attributes, we may generate keys also. What is a key means? An attribute or set of attributes determines all attributes of the relation. Then the left hand side will be considered as a key actually. So no FD inference rule is not like arithmetic multiplication. So you remember that it is not a multiplied actually. Now the question is, can we now infer SD determines CSDPQV? That is, J can be dropped on both sides or not. You observe here. In the previous example, what we got? SDJ determines CSJ DPQV. Can we drop J on both sides? That is, SD determines CSDPQV. No, it's not possible. So, no FD inference rule is available to get such type of because this is not arithmetic. You cannot cancel on both sides. Please observe that only using the basic Armstrong axioms or additional rules, union and decomposition, we may get new FDs, but not by applying our mathematical notations. You observe some more Armstrong axioms. For example, you would like to find F plus by applying the Armstrong axioms. If B contained in alpha, then alpha determines B is a reflexivity. Based upon this, we will get loan number determines loan number amount determines loan number amount determines amount, and so on and so forth. These are all reflexivity. Because subset in the previous example, on the right hand side is a subset of the left hand side. Loan number is a subset, amount is a subset. So then automatically we can consider those are derived FDs. Similarly, by using augmentation also, alpha determines beta, then gamma alpha determines gamma beta. Both sides we can add. So lone number determines amount means both sides if you can add branch name, you will get a additional dependency. Logically derived dependency, in other words. By using transitivity property also, if low number determines branch name determines branch city, then automatically low number determines branch city by using transitivity property. So, which are given and with which you are going to generate new. By using all such type of new or logically inferred functional dependencies, we can find our F plus, that is closure. So closure means all possible FDs logically derived or inferred from the given set of FDs F is known as closure of F. How to compute this closure? Because if you are using a brute force method, it's keeping on adding and we need to check every time. So how to compute a closure and what is the role of this closure in our process of renormalization will be discussed in the next session. Thank you. Thank you for watching this video.
Like, share and subscribe. Hit the bell icon for more updates.